Diogo. Uh, and while Diogo is getting ready for his presentation and sharing his screen, let me say a few words about his background. Diogo Ferreira, he received his electrical and computer engineering degree and the master's degree also from the Instituto Superior Técnico, IST, University of Lisbon, Lisbon, Portugal, in 2017 and 2019. And then since 2020, he's been with EDP Innovation in the Smarter Grids Department, Lisbon, Portugal. He is currently a doctoral student in the Department of Electrical and Computer Engineering at IST, University of Lisbon, Portugal. So, Diego, please go ahead.
Hello. Thank you for your kind introduction. My name is Diogo, and I'm here to present the paper Optimal Meter Placement in Low Observability Distribution Networks with DARE. Can you see perfectly my screen? Is the voice
yes.
Okay?
Yes.
Okay. So recently, policymakers have been promoting the decarbonization of the energy sector. As part of this process, it is expected a massive integration of distributed energy resources. However, this comes at a cost. Distribution system operators now need to adapt to a new situation for which distribution networks were not designed. And for that, there is the need for an efficient monitoring of the system. For that, it is required to acknowledge the old and the new restrictions posed by the system, such as load and their volatility, and the widespread use of pseudo-measurements. So the question imposes itself: how to improve state estimation accuracy in distribution networks? Well, to answer that question, we first need to consider the meter placement problem, which was first introduced by Schwepp and Wiles in their seminal paper. This problem can be defined as the choice of the type and accuracy of meters to be placed, as well as their location. And according to Schwepp and Wiles, the covariance matrix of the state estimate has a vital role on meter placement, and consequently on state estimation. This was a valuable lesson we took from the paper. Regarding the meter placement problem, some of its objectives include maintaining the system observable or determining how to decrease state estimation errors. This paper focuses on dealing with the old and the new restrictions posed by the recent changes on distribution networks, such as load and their volatility and the widespread use of pseudo-measurements. For this reason, this paper proposes a mixed integer linear programming method to find the optimal meter configuration for a network. To deal with the above restrictions, this method can deal with a variable amount of real-time measurements, and it can propose solutions based on the uncertainty expressed by multiple load and their scenarios. The meter placement approach used in this paper is the weighted least squares, which became widely popular due to its ability to favor some measurements more than others, which is particularly useful in this context where there is a limited number of high accuracy measurements. But how can we evaluate state estimation accuracy? Well, if we go to the seminal paper of Schwepp and Wiles, we can see that the covariance matrix of the state estimate has a vital role on meter placement, and as such can be referred to as the covariance matrix of the state estimate, as it can be interpreted as a measure of state estimation accuracy. But the problem is that to find the elements of this covariance matrix, we need to perform a nonlinear operation. To deal with this issue, Shen et al. Explored the similarities between the gain matrix and the admittance matrix. By considering that they are both symmetric sparse matrices, we can find a circuit representation for the gain matrix as we would for the admittance matrix. And the remaining issue is to know how to compute the elements of the gain matrix. For that, we can use this expression used in the weighted least squares to find the expressions of the admittances for the meters to allocate. For instance, If we consider a line model that follows the general two-port pi model with negligible shunt admittances and a state vector composed by bus voltage magnitudes of the network, we can find the admittance of the voltage magnitude meter, which corresponds to a shunt admittance that only depends on the accuracy of the meter, and also for the current magnitude meter, which is a branch admittance that depends not only on the accuracy of the meter, but also on the parameters of the branch. Before we go into the MILP formulation, just wanted to provide some background on the scenario generation used in this paper. A scenario is defined as the set of power measurements obtained at each bus under a determined time interval. And this figure illustrates a possible procedure to obtain those scenarios. For instance, if we consider the same time instant at different load profiles, for example T1, we can capture the load level at that time instant and store them as a scenario, as we did in this table. And we can do this for time T2, time T3, and so on and so on. So, regarding the MILP formulation, the original MILP formulation is an extension, the proposed MILP formulation is an extension of the original MILP proposed by Shen et al., this time to deal with the uncertainties expressed by multiple scenarios of different load and their profiles. For this reason, the proposed error index is the minimization of the summation of all diagonal elements of the scenarios considered. But for all scenarios considered. But now remember, we still have the problem of the nonlinearity. And for that, we can start by decomposing the gain matrix into a summation of gain matrices. G0, which holds the information of all measurements previously allocated, and this summation that reflects the possible contribution of each meter that can be allocated. Bk is a binary decision variable that refers to the allocation or not of each meter. After some manipulation, we can find this expression where we can select the nonlinearity using the instrumental vector zk. Finally, by applying the disjunctive model proposed by Bayes et al., we can find the intended result without any nonlinearities. When there is allocation, Bk is equal to 1 and there is an admittance. When there is no allocation, Bk is equal to 0 and there is no admittance. The remaining constraints refer to the maximum number of meters that can be allocated, the cost of allocating those meters, and the initial position of the meters, if applicable. The case study used in this paper is a radial 9-bus test feeder that is applied in 3 different situations. These situations differ on the number of scenarios, the presence of DARE, and the use of simulated or real data. The first situation has 2 distinct scenarios, one without DARE and the other with DARE. So the first step is to find the optimal meter configuration for each of these scenarios, and then for both, the compromise meter configuration. After that, we can compare their performance. So what we verify is that, for example, if we pick the optimal meter configuration designed for the scenario without DARE, and we apply it on the scenario with DARE, is that there is an significant increase in the error index variation. In the same way, if we apply the optimal meter configuration for the scenario with DARE on the scenario without DARE, we can see that there is also a significant increase in the error index variation. But what we also verify is that when we apply the compromise meter configuration to each of these scenarios, the error index variation is significantly lower. And this can be further verified through the analysis of the state estimation accuracy obtained at each bus under each scenario. For example, on the scenario without DARE, we can see that the optimal meter configuration designed for this scenario has the best performance overall, the red curve. The optimal meter configuration designed for the scenario with DARE has the worst performance overall, and the compromised meter configuration, as expected, stays in between the two of them. A similar result can be seen on the scenario with DARE. In this scenario, the configuration designed for this scenario has the best performance, the blue curve. The red curve has the worst performance overall, and the compromised meter configuration still stays in between the two of them. Now, this logic can be further extended by considering a larger number of scenarios. This time we consider two distinct situations with each 24 distinct scenarios. The first situation has low DARE integration and reflects the current situation of our network. And the second situation refers to a high DARE integration situation that reflects the predicted future of our network. So we follow the same steps as we did in the first situation. First, find the optimal meter configuration for each individual scenario, and then compare them with the performance of the compromised meter configuration, which is the optimal meter configuration for the whole 24 scenarios. This is displayed here. So what we verify is that 13 out of the 24 scenarios used in this situation actually choose as their optimal meter configuration the compromised meter configuration. And the remaining do not choose an optimal meter configuration that increases significantly the error index. On the contrary, on the high DARE integration situation, only 2 of the scenarios actually choose as their optimal meter configuration the compromised meter configuration. And more than 50% of the scenarios choose as their optimal meter configuration an optimal meter configuration that increases significantly the error index. So this is a warning to take into account for the design of the final meter configuration, the total amount of scenarios, and not just a few, particularly when there is a high DARE integration situation. To bring to a close this presentation, this paper proposes an optimal meter placement approach that is able to mitigate the impact of net load volatility on state estimation accuracy. And the main results indicate that if only one scenario is used to find the final meter configuration, state estimation standard error can increase significantly. Furthermore, a compromised meter configuration can be found to mitigate the effect of net load volatility on state estimation accuracy. And finally, the use of this compromised meter configuration will become increasingly relevant over time as there is an increase in the penetration of distributed energy resources in distribution networks. Thank you.
Thanks, Diogo, for your presentation. We have a couple of questions posted, so I would like to read them to you one at a time. The first one is, how is the error in the objective function calculated? Is it the absolute value of the error or the square of the error?
I did not follow the answer. The question.
Do you have access to the question answer page here?
Okay. Yes. How is the
maybe you can see it there.
Yes. So yeah, this is the square error. Yes.
Okay.
Yes.
Okay, so let's continue on to the second one. Do you consider a three-phase grid, or you use the single line equivalent? Why the DER affect the result? And in parentheses, he's asking, is this consistent with Schweppe's opinion?
Well, we use the single line equivalent. We did not yet approach the three-phase grid, but I believe that can be a path that we can follow in future work. Thanks.
Okay. There's another question. Could only include an unequal weighting of the scenarios, since it's probably more important to detect, for instance, voltage violations rather than having the lowest RMSE.
Yes. Our approach is versatile in the way that it can deal with the variable amount of scenarios. It can deal with the likelihood of scenarios. There are many ways that you can provide the application of those scenarios. And of course, we can weight those scenarios. We can manipulate the objective function. We can, for example, put the same scenario 2 times, 3 times. We can take into account that that point, which is very well pointed out.
All right. Well, thanks again. Those are the only questions we received. Yeah. Thanks again, Diego.